Hello, astronomy class. Happy Monday to you. We are almost done with school this year. It's crazy to think we've only got 3 more weeks left. Exciting. And I'm excited for the last 3 weeks of our class. Let me give you a little quick overview on what to expect. Sorry, if it's loud. I have my window open and I'm sitting next to the street. Um, so, a little overview of what to expect for the next 3 weeks of our class. I'm excited. We're going to spend a couple of days this week just wrapping up the life cycle of stars. That's the unit that it's called. And we're going to talk today about star leftovers, and that's kind of the last little presentation that I have. And then for the rest of our class, we're going to talk about kind of big picture questions about where did everything come from? What can we use science to do to help us figure out questions to where did everything come from? What did it all begin as? We're going to be looking at the Big Bang Theory and figuring out why scientists think that the Big Bang Theory is the best explanation for how our material universe came into existence. And so we're going to think about how maybe God may have used the Big Bang Theory or may have used things in this world to create our Earth and how he got how he created the universe. I guess is the big question we're going to be looking at for the rest of our class together. So, but today we're going to just focus on one last piece of the puzzle for the life cycle of stars and what is happening in the universe, and that is with star leftovers. So let's jump right in. Remember that most of the universe that we can see is made up of stars, and stars are having this constant battle between gravity and pressure. Gravity will push in and bring a star closer together, and I meant to update this, and we call this balance hydrostatic equilibrium. That's the balance between gravity and pressure from fusion. And so when a star runs out of fuel, when a star comes to the end of its life, the pressure from the fusion goes away. So this arrow diminishes, and gravity is allowed to contract a core of a star into smaller and smaller pieces. So we're going to be talking today about the leftover cores. So usually when a star dies, the star is really big and the core is really, really small right there in the middle. So usually when a star dies, um, the outer layers will fall into the core, bounce off that core, and explode. Right, and that's either for a low mass star, we call it a planetary nebula. For a high mass star, it's called a supernova. Okay, so that's fine. That's what the explosions are. But we're going to look at the dead cores. Today we're going to just zoom into those tiny little cores that are left behind. And when we do that, we find some really weird stuff. Okay, so the first thing that we're going to look at is for a low mass star. So when a low mass star dies, the core is made up of carbon atoms. Carbon is what's fused, helium fuses into carbon, and these carbon atoms are pushed together by gravity. And for a low mass star, gravity is just strong enough to push these carbon atoms together until basically there's no more room. It's like social distancing is just completely useless at this point because these atoms have been pushed together as close as they possibly can go. And this is what the result is. If you guys know the Jimmy Neutron model of an atom, where you got a nucleus and you got the electrons going around it, that's what we have here, where these atoms have been pushed so close together that their electrons are basically touching each other. The orbits of their electrons are bumping against each other, and we call this electron pressure. When the electrons don't want to get any closer together, they have exerted this kind of electron. It's called electron degeneracy pressure. I just call it electron pressure. And basically, the atoms don't want to get any closer together. They can't really because the electrons are resisting getting any closer together. And this is what a white dwarf is. It's basically this really, 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 really dense ball of carbon atoms that don't want to get any closer together. And so a white dwarf is very, very dense, and it's also really, really hot. So it's really small, really hot, really dense, and that's what a white dwarf is. And actually, if you take a star like our sun and you compress it down into the density of a white dwarf, it would be about the size of the Earth. So take the entire sun, compress it to the size of the Earth, and that would give you about the sense of how dense a white dwarf is. It's really, really, really dense. Another way to imagine this is a white dwarf is so dense um, that if you took the entire Empire State Building and collapsed it down to the size of a dishwasher, that's how dense a white dwarf is. So the entire Empire State Building, just imagine looking up at the Empire State Building, condense it down to the size of a dishwasher, that's how dense a white dwarf is. It's so dense that if you took a teaspoon of white dwarf material, it would weigh 30,000 pounds. It's about the size of 15 cars. So just like incredibly dense. Just imagine just being around this kind of object. It's like got such extreme gravity, it just kind of warps reality when you're close to it. That's what a white dwarf is. It's really, really interesting. Now, we're going to take it a step further. If you're a higher mass star, the core has so much gravity pulling in, so much weight pushing down on this ball of carbon atoms that in a high mass star, this electron pressure is not even enough. And some weird stuff happens where these electrons get shoved into the nucleus of the atoms, and the nucleus of the atoms just all get bunched together, and they all become neutrons. So the protons that were there meet the electrons and they get shoved together and they become basically a ball of neutrons. It gets even more tightly compressed, and this is called a neutron star. So this is for high mass stars. So high mass stars don't leave behind white dwarfs. The core of a high mass star gets compressed even more until the electron pressure gives up and you get neutron pressure instead. And this is a big ball of neutrons called a neutron star. It's even hotter, even more dense. So if you look at like a picture of one of those, actually, usually when you compress something to the size of a neutron star, it starts to spin. When things get compressed, they usually spin, and a lot of times these neutron stars will have strong magnetic fields, and they'll have these kind of beams of radiation that go out from their magnetic axes, and when they spin around, they're kind of like lighthouses. So when you look out at the night sky and you see some of these flashing stars, they're actually called pulsars, and they're actually neutron stars that are just spinning really, really fast. So it's, I think I had this simulation's not working, but it's kind of like a lighthouse. Now look at a size comparison, okay? So if you take the sun and compress it down to the density of a white dwarf, this is what you would get. But if you compress it down to the density of a neutron star, it's so, so, so small. It's the same mass, but it's compressed down to the size of about a city. So take the city of Louisville as a whole and make it a bubble. That would be the size of a neutron star. Very, very dense. So that's really interesting. You got a white dwarf and you got a neutron star. But what if you could compress that neutron star even more? What if there was even more gravity pushing in? Is there anything that could break past this neutron pressure? So pushing in on these neutrons, you would think that there's nothing that you could do to break these down even smaller. But if you have enough gravity pushing on the neutrons, the most mysterious thing in the universe happens. The laws of nature just basically give up. There's no more pressure that's left, and mass is compressed into a single point, and a black hole is created. So that's what a black hole is. That's how black holes get created. It's whenever a star is so, so massive that the weight of the star compresses neutrons down to the point where the laws of nature just give up. And basically, we don't have any way to explain it. There's nothing left to push back. And gravity has created a singularity, a single point where all the mass is concentrated at that one single point. And that's what we call a black hole. When the density is so high, gravity is so strong that not even light can escape it. And this is how black holes are created. So if you have nothing to fight against this gravity that's pushing in so strongly, you get a black hole. Um, so really weird. This is what happens to the cores of high mass stars. Here's an artist rendition of a black hole. The gravity is so strong that even light gets bent around, and that's why it's having these kind of weird effects on the light around it. So, in summary, these are the three possibilities for the end of a star's core. You can either have a white dwarf, that's a low mass star, where the electrons have run out of room to move around the nuclei and they're forced into their lowest energy states, they're forced together. A neutron star is when the protons are forced to absorb the electrons and make neutrons, and then the nucleus of the atoms, the neutrons, are forced together here. And then a black hole is when the neutrons just completely collapse and nothing is left. These are the three possibilities. So let's complete the life cycle of the stars diagram here. Let's get my face out of the way. So to go back and review, stars all begin at a nebula, right? And then from that nebula, you get low mass stars and high mass stars, the main sequence low mass stars. So from a low mass star, when a low mass star dies, it becomes a red giant. And when that red giant runs out of fuel, you get an explosion, kind of a slow motion explosion called a planetary nebula. And so that nebula comes back to the beginning and forms a new nebula where more stars could form. And then the leftover core from a low mass star is called a white dwarf. Now, for a high mass star, when it ends its life a little bit quicker. It becomes a red supergiant, just bigger, right? It fuses atoms that are heavier than carbon all the way up to oxygen, nitrogen, silicon, neon, iron. And when it hits iron, it has a supernova explosion. And that supernova does three things. Number one, it spreads out these elements that it created to other parts of the galaxy. Number two, it triggers the birth of new stars. And then number three, it fuses atoms itself. It makes heavier atoms like gold and silver and those kind of things. So a supernova basically restarts the process, and it can even directly trigger the birth of some new stars. And then depending on how massive the star started out as, it could either become a neutron star, or if it was extremely massive, it could become a black hole. So that's our complete life cycle of stars diagram. You can see this is what's happening in the universe. This is how things are changing. This is the theory of stellar evolution. And I know I went really fast through all that just now, but I want you to see this big picture here of what's going on in the universe. God is creating new stars. He's creating new elements, and he does this through the process of stellar evolution. The theory of stellar evolution is the explanation that we have. And this also explains where we get white dwarfs, neutron stars, and black holes from. Gives us good explanations for basically everything that's happening beyond our Earth, beyond our solar system. This is the theory of stellar evolution. So one thing that's left for you to do today is complete a worksheet below. It should be pretty self-explanatory. You can come back, look at this video if you need to, and let me know if you have any questions. We're going to be taking a quiz probably tomorrow or maybe Wednesday over all this stuff, so just be ready for that. You can find a playlist of all the videos from this unit by scrolling up to the top of our Canvas homepage. So have a great day.